Hello, today we are going to talk about searching algorithms. We will discuss two algorithms for the searching problem. The first algorithm is the linear search and the second algorithm is the binary search. So what's the searching problem? In the searching problems, we have an array of n elements and we want to search for a value x in this array. Whether we want to see whether this value x exists in the array or not. So the output will be the index of the value x. If the value x is in the array, we want to know where it exists. Is it the first element or second element or element number 100 or so on. And if the x is not in the array, we also want to know this by returning the value of -1. So -1 means x is not in the array. And if the output of the algorithm is 10, this means that x exists at position 10 in the array. We have two algorithms to do this, to solve this searching problem. Let's start with the first one, linear search, and let's do it by the code. So let's do the searching. We'll create a new method called static void. It returns integer, it's not a void, and the name is linear search. It takes as input as integer, array of integer, let's call it a, and it takes the value x that we are searching for. So this is the linear search method. How it will work: first we will define a new variable. We will make a loop for all the elements in the array. I less than a dot length and I plus plus. So we loop over all the elements and we compare if a of I equals to the value x, then we will return I. We will return the index where we find x and we are done. But if we didn't find x in all the elements, at the end of the loop we will return -1. So simply this is the linear search algorithm. It's a very easy algorithm, just for loop, and we will go over all the elements and search for the value x. Now let's go back to the slide and try to analyze the linear search algorithm. So we have three types of analysis. First analysis is called best case analysis. In this analysis, if x was the first element, then the loop will only have one iteration. So in this case, we will have a running time of big O of 1. In the worst case analysis, if the element is the last element, then we have to go through all the elements in the array. Another possibility is x does not exist in the array. Again, we have to search for x in all the array. In this case, the worst case analysis is big O of n. And the average case analysis is that we find x in the middle of the array. So in this case, we need n over 2 steps. But this is, again, it's big O of n because we don't care about division by a constant in the big O notation. So in general, this linear search analysis needs big O of n, so it's not so efficient. So that's why we want to look for a more efficient algorithm. Here we have something called binary search algorithm. For this algorithm, the array has to be sorted. So we should have a sorted array so that we can apply this algorithm. And this algorithm is much more efficient than the linear search, as we will see. So how this algorithm works, let's assume we have an array and we are searching number 47. We go to the middle and compare 47 with this middle, 14. If this 14 is less than 47, then we know that the 47 will be in the next half of the array. So again, we are looking for 47, we compare it with 14, 47 is more, then we go to the next half, and again we divide it in the middle, we compare 47 with 45, then we go to the next half, and so on till we find the 47. So this is the idea of the binary search. We start with array, we divide it half, and we look to the value. Is it in the middle? If yes, then we are done. If not, we go to the half. We delete half of the array. We compare the value that we search with the value in the middle. If it's more, we know it's in the second half. If it's less, we know it's in the first half, and so on. So let's do the code. So here you will see that we will create another method, public static. It returns integer and the name binary search, and it takes again an array of integers. Let's call it a and integer x. So first, in this binary search, we will define the boundary of the array we are searching every time. So at the beginning, we will define a variable called low equals to 0. Low means where is the first index we will search in. So the first index is 0, and we will define high to be what is the last index we want to search in. It's a.length minus 1, which is the last index in the array. So if the array is 100, the low will be 0 and the high will be 99, the last index. And then what we will do, I will do it in one step, and then we will have a loop. Let's do it in one step. We need to define something called mid, the middle index. So mid equals to low plus high divided by 2. So I want to know what's the middle index. It's not height, it's high. What's the middle index of the array? So with this, I store it in a variable called mid. And now I compare if x is equal to if x is equal to the value in the mid, then I'm done. I just return mid, right? I found x. Else if x is not the value in the middle, but it's more, if x is less than a mid. So x is less than the value in the middle. In this case, I will know that I should search for the first half of the array. I should not search in the second half of the array because x is less and the array is sorted. So x is less than the middle value and the array is sorted. In this case, I need to modify the high. So I should not search from 0 to 99. I should search from 0, so low will be still 0, but the high, I will modify it to be mid minus 1. So with this, I am deleting the next half of the array. I am searching from the low, which is 0, to the high, which is before the mid point. So with this, I'm searching in the first half of the array. But what if x is greater than a.mid? So in this case, if x is greater than the value in the middle, then I have to search in the next half of the array. In this case, I need to modify low to be mid plus 1. So with this, high is the same, 99, but mid will be something like 50 or 51. So I'm searching from 51 to 99. In this case, I'm searching from between 0 and 49, something like this. So this is now the step. This is only one step. But I will repeat these steps. So every time I increase low or decrease high, I need to do that. I need to stop at some point. I will stop at a point where low is is greater than high. So as long as high is greater than or equal low, I will keep increasing the low or decreasing the high. Okay, so when I will finish once the high is more than the low. If the low is more than the high, I will stop. So as long as the high is greater than or equal low, then I'm still searching in the array. But if the high is less than low, then I'm done. I finished the array. So this is the while loop that will end this iteration. I will close this while. If I finish all the array and I didn't find x, then I just will return -1. So this is the binary search algorithm. So I make two methods, one linear search, the second is binary search. So let me try this two algorithm. Let me make an array, let's call it array equals new array. Let me make the size as something big, maybe 1 billion. So I make an array of integers of 1 billion integer, okay? And initially all the values of the array is zeros, but I don't care. I just want to try the two methods. So all the values are 0. I want to try to do two things. System.out.println. I want to try to use binary search. Let's start with linear search first. Linear search. I will search for the array R for the value, let's say 10. I'm searching for value 10 in the array. I will not find it because all the values are 0 at the beginning, but I don't care. I just want to see the performance of the linear search. So I should get -1 actually, because 10 does not exist in the array. I will do the same with binary search. Binary with B small. Again, I will get -1 in the second one. Let's try. This number is too much for my small memory, so let me do it like this. So now I'm as expected. I'm getting -1 and -1 for both searches, right? Because 10 does not exist in this array. So now I want to measure which one is faster. So we have something in Java called system.nanotime. So this gives me the nanotime at the time of this instruction. Let's store it in long starting time. So I just store the starting time before I start linear search, and also I need to store the end time, the ending time, after the linear search, okay? And then I will print something system.out.print line. I will print how much time did it take to do the linear search. So it's ending time minus starting time. This all divided by, so this will give me the time in nanoseconds. If I divide it by 1000, I will get it in microseconds. Okay, so with this I will get printed how much time did linear search take in microsecond. Okay, I will do the same for binary search. So I will just copy these two instructions. No, this instruction I don't need starting time. I will change the starting time to be here, and then the ending time I will change it, and then after the binary search. So with this I'm printing two values: the time that I need in linear search in microseconds, and the time I need for the binary search in microseconds. So let's see. So you can see, like, binary linear search, it needs 200,000 microseconds to do the search, but binary search I only need 39 microseconds to do the binary. So the binary search is much more efficient. And why is that? Let's analyze the binary search. So this is the code we did together. So binary search, if you think about how the binary search is working, every comparison we do, we divided the search space by 2. We divided the array into two sub-arrays, and we ignore one half of the array, right? So if we start with array with 32 elements, if we do one comparison, then it's 16 left. If we do another comparison in the middle, then we only have 8 to compare with. If we do another comparison, we only have 4, 2, 1, and so on. So for 32 comparison, we only need 5 comparisons. So this behavior looks like the log n behavior, because log 32 is 5. So actually, the running time or the time complexity of the binary search is big O of log n, which is much faster than big O of n, which is the linear search. Because in the linear search, if you have 32 elements, you have to compare with all the 32 elements. But here I only do 5 comparison. So this is much faster, and we saw that in the code that it needs much less time for binary search to do than in the linear search. But remember, the array in the binary search has to be sorted. So as exercise, please implement the linear search yourself and implement the binary search as well using iteration. So we need the iterative method. This is what we did in the slides on the NetBeans. But we also need you to do the recursion. So you can do also binary search using recursion. See you in the next video.